medicine seminar series. And it is a great pleasure to welcome Dr. Chris Bian as our speaker today. So in fact, Dr. Bian completed a PhD here at McGill University. He was co-supervised by Dr. Erica Moody and Dr. Sahir Bhatnagar. That was relatively recent, actually. And he's going to talk, I think, about some of the work from that time, from his doctoral degree. But he is currently a postdoctoral fellow, and he is at the Miami Herbert Business School in Florida, where he's working with Dr. Lan Wang. So with that introduction, I would like to invite Chris to go ahead. And I should also just note that he has asked that questions be kept for the end rather than during the middle of the talk. So please go ahead.
Yes, thank you very much for the introduction, Celia. So I'll just start. Okay, so thanks very much for inviting me. And today I'm going to talk about my research in variable selection for individualized treatment rules focused on discrete outcomes. And this is a joint work with my PhD supervisor, Eric, Sahir, and Susan. So I'm going to first start with precision medicine. So as you can see here, we got two graphs, where the first graph, we have this, each graph represents a treatment strategy. And the first graph, we have this one-size-fits-all approach. So as you can see here, we just assign all the patients the same treatment B here, where ignore their information. So perhaps this treatment B is the cheapest, or the treatment B has the best performance on the overall population. And in this second graph here, we have this individualized treatment regime. So basically, we are assigning treatment according to patients' characteristics. So for those flu patients, we assign treatment A. And for those, accordingly, for those orange patients, we assign treatment C. So the main idea here is to improve individual patients' health outcomes by tailoring medical treatment to each patient based on their information, such as sex or gender. So why to do this? Because there exists heterogeneous treatment effects among individuals. For example, maybe there is a case that elderly patients, they have side effects, but not younger patients. And also maybe the treatment is better for female patients. So in such a case, treatment decision should be made based on sex and age. And there are also other reasons. So overtreating will yield side effects, poor compliance, and high costs. On the other hand, undertreating will have suboptimal health outcomes. So in this way, treatment decisions need to be tailored to each individual instead of a one-size-fits-all approach. That is, the treatment decision should be a function that maps patients' covariates to the treatment space. And individualized treatment rules, ITRs, it can help us achieve this goal. So now I will introduce some notations. In a single stage ITRs, the observed data are X, A, and Y, where X are the patient's baseline covariates, and A is a binary treatment received, and Y is the patient's outcome. Usually, we prefer a large value of Y. And the objective of ITR and precision medicine is to find the optimal treatment regime such that the expectation of this YA is maximized, where this YA here is the potential outcome. That is the outcome of the patient. We assume that the treatment A has been taken. So this potential outcome is a conceptual idea. And the fundamental problem in causal inference is that we can only observe one potential outcome for a specific patient. For example, if this patient has taken the treatment A, then we can only observe Y1. The Y0 is not observed, it's missing. So some motivations, why do we need to do variable selection in ITRs? Because in ITRs, the collected data often contain many irrelevant variables for tailoring treatment, and including all those variables in the analysis could yield first a loss of efficiency. That is, the resulting estimator could have a large variance. And second, it could also have an unnecessarily complicated treatment rule, which is difficult for physicians to implement or to interpret. So variable selection for ITR is very important, and it has been studied in several literatures focused on continuous outcome case. However, relatively few methods exist for discrete outcomes. So we noted here that applying existing variable selection techniques to ITRs directly is challenged. First, because the aim is different, because variable selection for ITRs aims to improve the decision rules rather than the predictive performance, which is a goal in the traditional statistic literature. And also in ITRs, we are most interested in selecting variables that may be effect modifiers. So to see this, let's see an example. So for us, in this example, the outcome regression looks like this. However, we are only interested in this X2 because it's the effect modifiers. And as you can see, because of this interaction, only X2 is useful for making treatment decision. This X1 is useful for predict the outcome, but it's not useful for to make treatment decision. So we are not interested in X1. We are only focused on this X2 here. And the second challenge is that ITRs, they are often estimated using semi-parametric methods. So semi-parametric methods, they are difficult to extend to a regularization framework, and especially for the discrete outcomes due to the non-identity link functions. We will see that later. So to provide robustness against model misspecification, ITRs are often estimated using estimating equations or estimating functions. So now we denote U theta, which is a p-dimensional vector, as an estimating equation. The parameter theta can be estimated by solving this equation. However, the resulting estimator by solving this equation has no sparsity. That is, we cannot do variable selection. And there are two ways to achieve sparsity in the use of estimating equation. So the first one is to use the Danzig selector, where the estimator can be obtained by solving this constraint optimization problem. So the authors call their method Danzig selector because this constraint minimization problem can be solved efficiently by using linear programming. And George Danzig is the father of linear programming. and that's why they have this name. And also we could use the regularized estimating equations. So instead of setting u theta as 0, we require it to equal to the guy in the right-hand side, where lambda here is the tuning parameter. And this Q function here is the subderivative for some penalty function. So let's see an example. The lasso is a special case of REE. So recall that the lasso, the first order condition of lasso is to solve this, where the left-hand side is just the normal equation. So if we want no sparsity, we just set this left-hand side to 0. And the right-hand side is the subderivative of the L1 penalty. That's the penalty function of the lasso. So okay, we know we can use those two methods to introduce sparsity. However, although the DANZAG and REE, they can work well for continuous outcomes, their implementation can be difficult for discrete outcomes. Indeed, because of the existing estimating function to estimate ITRs are nonlinear. So the consequences are, first, the DANZAG selector cannot be solved using linear programming anymore. And as for REE, it has been studied in several literatures where they all use the linear quadratic approximation to solve the REE, which is very computationally burdensome because first, it requires the calculation of the Hessian matrix. Then it also requires the calculation of the inverse of this Hessian matrix. So it's very computationally burdensome. It will take a lot of time to calculate it in a high dimensional setting. And finally, even if all those solutions can be found, it's very challenging to select the tuning parameters because as I mentioned before, we're not focusing on the predictive performance. So some popular tuning parameter selection techniques, such as a kayaking information criteria or the cross-validation, they would fail to select the best tuning parameter. Okay, to estimate ITRs, we first need some assumptions. Those are traditional assumptions in causal inference literature. The first one is the stable unit treatment value assumption. It states that the potential outcome of a unit is unaffected by others' assignment of treatment. So basically, we assume that there is no interference. And the second one here is the consistency assumption. So the potential outcome of YA is equal to the observed outcome if the observed treatment is also A here. So this assumption allows us to connect the potential outcome with the observed outcome. So as such, many estimates can be identifiable from the data because of this assumption. And third, we have the conditional exchangeability or no unmeasured confounders assumption. So it says that conditional on this X, on this subpopulation, or this subpopulation, we have the potential outcome is independent of the treatment assignment. So basically, we are mimicking a randomized experiment in this subpopulation. So we all know that in medical research, we love randomized trial because in that word, causality is equivalent to association. However, in many applications, we don't have the randomized trial, and that's why we need this assumption, conditional exchangeability. And finally, we would require positivity assumption. So for any patient, it has a positive probability, to either receive the treatment or not receive the treatment. And moreover, we would need some assumptions on the model. So we assume that the relationship between y, x, and a can be captured by this semi-parametric model. So G here is a known link function, and F0 is an unknown baseline function. And gamma here is a known function which is referred to as the Blip function, and it can be written as the difference between those two guys. So in the first term, we set the potential outcome as YA, and the second term here, we set it as the 0. So we are interested to compare the difference between those two. So recall that we have this relationship. So in this model, F0 is irrelevant for making treatment decisions. Hence, it's a nuisance model. And clearly, our parameter of interest is psi here. The psi in the Blip model here. And we call this psi the Blip parameter. So recall that our aim is to maximize the expectation of this term. And to maximize this, it's sufficient to simply just maximize the Blip function gamma. Okay, let's see an example. If we assume that the Blip function is linear, that is in this form, then the estimated optimal treatment rule is just simply in this form, where this I here is the indicator function. So let's see why. So if this term inside this parenthesis is larger than 0, then the treatment decision should be A equals to 0. In this way, we will always have a positive value of the Blip function. However, if this term inside this parenthesis is less than 0, then we could just simply set in A equals to 0. In this way, we could avoid the negative value. And that's how we get the estimated treatment rule. So, okay, we have just seen that to make the treatment decision, it suffices to estimate the Blip parameters. And now I will briefly review some methods to how to estimate the Blip parameter. The first method is the outcome regression. So we just simply regress y on A and X, and then the Blip parameter can be estimated. However, this requires F to be correctly specified. Or you could simply think it that we require the likelihood function to be correctly specified. And second, we could use the propensity score model to estimate the Blip parameter. So it's sufficient to estimate this conditional probability. And finally, we have this doubly robust method. It combines the first outcome regression and the second propensity score model. However, it only requires one of them to be correctly specified to achieve a consistent estimation. And in this talk, I'm going to focus on the doubly robust method. So from now on, I will denote X psi as a covariates in the Blip model. And I will denote X beta as a covariates in the baseline model. Suppose that the log link is used. Then the A-learning estimating equation proposed by Robbins looks like this. So here we are using two plug-in estimators. The first one is pi hat here, propensity score model. And the second is the beta in the baseline model. So those two models are all nuisance models. However, we would need to first estimate it, then plug into this estimating function, then solve the psi here. So recall that I mentioned that the A-learning estimating equation is difficult to generalize to a penalized framework to do variable selection. So in this work, we propose new estimating function for count outcomes. And we show that the newly proposed approach can be easily generalized to a regularization framework. So for count outcomes, we present this U2, the new estimating function. This new equation takes a similar form to U1 with this term here, the same. So one might ask, what's the advantage of this equation? Why should we use this? So it turns out that if you treat this term as a constant here, then this U2 equation is basically a estimating function for generalized linear model for count outcomes. And with this term as the weights. So it's a weighted generalized linear model estimating function. However, noted here that this exponential term here is actually not a constant because it contains an unknown parameter psi here. In this way, we propose to solve this estimating function in an iteratively way. So first, we assign a random value for psi in this term here. Then we keep updating to solve this equation, keep solving the psi in this term here. And we keep doing this iteratively until the convergence. And that's why we called our method iteratively reweighted generalized linear model. Okay, so now we are ready to present the first result in this talk. First, we need this assumption. When at least one of the two nuisance models is correct. So recall that pi is the propensity score model and F is the baseline model. We assume that there exists a unique population parameter theta star such that U2, the new proposed estimating function, is an unbiased estimating equation. And now we have this theorem. Assume that all the causal assumptions hold. If the posited baseline model satisfies this condition, Xi is a subset of the X beta. That is, the covariates in the Blip model is contained in the covariates in the baseline model. Then we have psi star equals to psi 0, where psi 0 is the underlying true Blip parameter. So this theorem suggests that the resulting estimator obtained by solving this U2 is also a double robust estimator, which says that our newly proposed estimating function also have a nice property. Okay, so now we're ready to introduce sparsity, how to do variable selection. To do so, we also pursue an REE approach, regularized estimating equation, to introduce sparsity. So the ITR REE require finding the solution of this guy. And again, on the left-hand side, it's just the U2 estimating equation. And on the right-hand side, this is the subderivative of the penalty function. And a natural problem rises, how to choose the penalty function Q. So the choice of the penalty function to estimate the Blip parameters consistently requires that the penalized model satisfies no false exclusion of tailoring variables. or a stronger condition is the variable selection consistency. And second, we also require the selected model has a strong heredity property. That is, psi j can be estimated non-zero only if the beta j is non-zero. And this is equivalent to the condition we posted before. Xi is a subset of X beta. So many penalty functions, they could have the selection consistency, such as lasso, scat, or the adaptive lasso. They could achieve the first one. However, they all fail to achieve the second assumption, the strong heredity property. And in this work, we modify the adaptive lasso penalty and show that not only the strong heredity can be met, but also can decide the Blip parameter can be unbiasedly estimated. So suppose that we have some initial estimators such that they are square root n consistent. And then we can construct our adaptive weights as follows. So for the adaptive weights corresponding to psi, we just constructed using adaptive lasso. However, for the adaptive weights corresponding to beta, we constructed using taking a maximum between beta j and psi j here. As such, for non-zero psi j, both wj psi and wj beta, they will also converge to a finite constant. And as such, beta j and psi j hat, they can always remain in the model. And we could always have the strong heredity property. And another nice property of using this kind of adaptive weights is that by the oracle property of adaptive lasso, this penalized estimator, it's also a doubly robust estimator. And also it has a limiting distribution of a normal distribution. Yeah, so that's why we need, that's why we construct this penalty function here. So now we present an approximation to solve the ITR REE in just one step. Suppose that once again, we have this initial estimator. Then we could just simply plug in this initial estimator to this term here. And we could simply solve this whole penalized generalized linear model problem. And there are many R packages could do it. For example, the GLM is in R. And we haven't talked about the choice of the initial estimator. And we suggest that to use the solution of the unpenalized U1 or U2 as the initial estimator. And under mild conditions, using the plug-in estimator here, we have a negligible effect on the resulting estimator. Okay, finally, tuning parameter selection. So the choice of the lambda, it plays an important role in REE. And in penalized likelihood, the optimal lambda is often chosen in a way such that the corresponding model has a lowest information criteria or a lowest estimation error. So for example, AIC, BIC, or cross-validation. However, this method, they would fail if the likelihood is misspecified. And another approach is to replace the likelihood part with this value function here. So you can see here, this approach, it requires the estimation of the propensity score model. So this alternative approach, they could work only if the propensity score model is correct. So now I introduce our proposed method. Recall that our method could be viewed from a minimization perspective. Yeah, because basically we are solving a penalized generalized linear model problem. So naturally, we propose to select the tuning parameter by choosing the model that has the smallest value of this guy. Where d lambda here, the first term is just the quasi-deviance. And this S lambda is the number of non-zero components. And kappa n here is just some positive sequence. And in AIC, this kappa n is 2. And in BIC, the kappa n is just log n. And in this work, we suggest to set kappa n as log n log p, following this nice paper. Okay, a quick summary. So in this work, we propose new doubly robust estimating function to determine an ITR when the outcome is discrete. And we show that this newly proposed approach can be solved efficiently using a weighted generalized linear model, iteratively. And we also show that this newly proposed method can be easily generalized to a penalized framework, which can estimate the ITR and selecting the important variables simultaneously. And finally, based on this, we present a simple approach to select the tuning parameter. And finally, some future work and some directions. The first one is how to choose the initial estimator in a high dimensional setting. So to obtain a double robust estimator, we need a well-behaved initial estimator. And in a high dimensional setting, we could build on idea in Huang, this paper, who used the marginal regression to obtain the initial estimator for adaptive lasso. That is, the outcome is regressed separately on each variable. So for example, if we have the outcome is y, and we have two variables, x1 and x2, the marginal regression is that first we regress y on x1, and next we regress y on x2, in this way to obtain the initial estimator. However, this technique is more challenging in our ITR setting because it violates the assumption that the Blip model is correctly specified. And also some violations of the causal assumption. The first is that what if we have the unmeasured confounders? In this case, we could use proximal causal learning, or we could use the instrumental variables approach. And the second violation is that the silver assumption is not held, which means that now we have the interference. And I believe that we could combine our paper with the framework in this paper and to solve this issue. Another interesting topic is how to generalize our framework to a multi-stage setting. So we could borrow the framework in reinforcement learning literature. For example, we posit Markov assumption or conditional mean independence assumption. And we could model the Q function using flexible non-parametric method. And once we obtain the Q function, we can accordingly to make treatment decisions at each stage. And finally, some connections with the panel data in econ literatures. So the panel data in economics are closely related to our DTRs or ITR setting because they both consider the longitudinal data case. However, in panel data literature, they seldomly consider the dynamic effect. So it will be of interest to combine commonly used models in econ to DTRs, such as fact model or two-way fixed effects model, or maybe even the matrix completion. Okay, that's it from me. Thank you very much for your attention.
Thank you very much, Chris. I want to ask if there are any questions. Feel free to put a question into the chat if you wish to, or you can also turn on your microphone and ask a question. I can start off actually by asking, did you try out these methods in some kind of data sets, and if so, what kind of data sets did you use? Did you try out?
Yeah, we tried it on a small sample size, which only have 50 number of observations, and the number of predictors are pretty large.
And what's the computational speed like?
The computational speed is pretty good, yeah. It's basically because we're basically using GLM net, to
fit the penalized models.
Yeah.
So do you think it would scale up nicely to larger sample sizes or larger numbers of variables?
Yes, I believe so. But as I just stated in the discussion, how to obtain because our method require initial estimator, and we obtain the initial estimator using by solving the unpenalized estimating equation. So how to obtain the initial estimator in a high dimensional setting? This is a challenge, and we are working on it.
Julian.
Yeah, well, thanks for the talk, Chris. I really appreciate it. I think it's kind of helpful to understand all the theory behind some of the methods that I focus on, which is mostly application-based of similar theories. I was just hoping if you could, over the course of the talk, I just heard a number of similarities and assumptions as well as derivations between your method and Mendelian randomization. So I was just wondering if you would be able to maybe contrast what you did with Mendelian randomization a little bit, if you know what the method is.
Sorry, can you say that again?
Oh yeah, I'll just bring my mic.
The question is that to compare my method with Mendelian randomization.
Yeah, if you're aware of Mendelian randomization, like it's a little niche.
Actually, I'm unaware of it. Yeah, sorry.
Okay, no worries. But thanks for the talk. It's very enjoyable.
Thank you.
Are there other comments? So, if I go back to Julian's question, that Mendelian, we could think of it as having some very good variables, X, I think in your notation, that will predict A.
So yeah, I think Mendelian randomization
so you would have genetic variables that would predict the intermediate variable A.
Yeah.
So, but I mean, I guess a corollary is, what if you don't have good variables to help you build the robustness that you need?
So which means we may have unmeasured confounders.
Yeah, that's right. Yeah. What
So
happens
yeah,
in those kinds of cases?
so in that case, our method would fail. But again, we could use instrumental variables, to save the case.
Mm-hmm.
And I believe that Mendelian randomization is also commonly used in causal inference on the use of instrumental variables.
Yeah, exactly. Exactly. Yeah, exactly. It's a instrumental variable technique. Yeah. And I guess the other question that I might have, which was more about the penalties. Obviously you talked about the fact that you might be able to use different kinds of penalties. Are there any limitations on the kinds of penalties that you could apply? Do they any sort of constraints on what that penalty form needs to be?
Yeah, we could use many penalty functions. However, such as SCAD or the adaptive lasso.
Yeah.
So we're using adaptive lasso here because adaptive lasso penalty it requires initial estimator, and our method also needs an initial estimator.
Mm-hmm.
So naturally, that's why we consider the adaptive lasso. But the drawback here is again it requires the initial estimator. So in high dimensional setting, it will be challenging. And also, I just mentioned SCAD. SCAD it doesn't require initial estimator, and it has some nice theoretical property, such as oracle property, and it doesn't need to impose such stronger condition like adaptive lasso. However, we found that that there is no R package for SCAD, to employ the weighted penalized likelihood approach. So that's why we didn't choose SCAD.
Yeah. So the fact that you have to have starting values is a bit of a limitation, and it's sort of I run into data sets, so does Julian for that matter, where P is much bigger than N. So then you can't get a starting value with any simple approach. And you mentioned some of the potential solutions, but have you played with them? Have you tried them out? Have you explored them a little bit?
I haven't tried them out. Yeah.
Okay.
These are just some directions. I believe they could work, but I haven't tried them.
Are there some other questions from those who are here? In that case, I'd like to give you a warm thank you, Chris, for this interesting presentation today and challenging us to think about causal effects versus confounding effects. And thank you again for the presentation and in stimulating the students today. Thank you.
Thank you very much. Thanks, Celia.
Bye-bye.
Bye-bye.